recurrence coefficients for orthogonal polynomials with respect to logarithmic weight.
Okay. Happy birthday, Jeremy. Okay, and thank you very much for the invitation to speak here. So this work involves two papers. The first was work with Oliver Conway over here. It's in Sigma. And the second was together with Mateusz Piorkowski. It's also in Sigma. So to start off, really, I didn't quite know what to assume people know about orthogonal polynomials, so I'm just going to give a story about it. So recall the following basic result from the theory of orthogonal polynomials. So let T be a bounded Jacobi operator, tridiagonal, real numbers down the diagonal, positive numbers off the diagonal, which acts on L2 of 0, 1, 2, 3, so on. So now there exists a unique probability measure mu with compact support such that E0, 1 upon T minus E0 is given by this Cauchy transform. E0 is the vector, which is just supported at the site 0. So d mu over here, let me go back, d mu over here, okay, there is the spectral measure for T in the cyclic subspace generated by E0, TE0, T squared, and so on. The map B taking a measure to a Toplitz or a Jacobi matrix T is a bijection onto the Jacobi operators. Now, if pk are the polynomials orthonormal with respect to this measure, then they satisfy a three-term recurrence relation of this familiar form. So we have the bk at the edges, the ak on the diagonal, and we have that, with the understanding that b of -1 is always taken to be 0. The AKs and BKs are called the recurrence coefficients for the measure d mu. Now, given a measure, it is of great interest to determine the asymptotic behavior of the ANs and the BNs as n gets large for the Jacobi matrix T, which arises from the measure d mu. So a lot of work, starting more than 150 years ago, with things about people like Legendre, for example, and continuing to the present day with great energy, has been done on this problem. In other words, the problem of evaluating the asymptotic behavior of the ANs and the BNs, and also a tremendous amount of work on the inverse problem, which is given a Toplitz Jacobi matrix T, analyze what the spectral measure is. That's the spectral problem. Now, starting in 215, A.Magnus began the study of weights which had the form d mu as Wm of x dx on the interval -1 to 1 with a logarithmic singularity at one end. More precisely, he considered weights W of mx which are smooth on the open interval -1 to 1, and for which Wm divided by 1 plus x to some power beta has a positive limit, so Wm looks like 1 plus x to the beta as x goes to -1. And Wm looks like 1 minus x times a logarithm. In other words, this ratio has a positive limit as x goes to +1. So you've got basically an algebraic type singularity at the on the left hand at the left hand point, and you have a logarithmic behavior at the point x equal to 1, and here you must have that alpha and beta are bigger than -1 to ensure that the measure is integrable. So based on some really remarkable numerical calculations, I just don't know how he really did it. It's when you begin thinking about this problem, you see how difficult it is to do numerically. But what he conjectured was the following. I don't know how he was able to separate out these different powers of n and the log, but from the numerics, he made the conjecture that for this weight m, with given alphas and betas, the asymptotics of the ANs, which are the diagonal entries in the Jacobian matrix, behave asymptotically like this. For some cons, so the alpha and the beta are the parameters on the left-hand side and the right-hand side. B is some constant, and C is some other constant. And this error term is 1/n squared log n squared. And the BMs has a similar kind of behavior, 1/2 the same B coming here, but without the 2, the same C, and again, error of that same size. For some constants B and C. In particular, for the case where just Wm is log of 2 over 1 minus x, so you've got a logarithmic growth at x equals plus 1, and when x goes to -1, you see you've got log of 2 over 2, so this has a 0 at the point x equal to -1. He conjectured in this particular case that b is 0, and c was this number -3 over 32. So we note here that alpha is 0, that is the, so let me just go, so alpha is this parameter here, which is connected with the behavior as x goes to plus 1, and beta is the behavior as x goes to -1. And so in that case, together with Piorkowski, we were able to verify this conjecture with a stronger form of the error term. So we showed that an equals 1/4n squared minus 3/n squared log n squared, and the error term is of order 1/n squared log n cubed. Bn has this behavior 1/2 minus 1/16 of n 1/n squared, 3 over 32 n squared, and with the same error term here. So you can check that this is exactly the prediction you would get with these alphas and betas. Then going back to the earlier work with Oliver Conway. There it is. We looked at WK of x as log of k upon 1 with 2, so k is bigger than 2. So this weight here still has a logarithmic singularity at 1, but at x equal to -1, because k is bigger than 2, this is strictly positive there, so there's no 0 at this point. So in this case, alpha and beta are 0, and you get the following forms of the which are exactly what Magnus had predicted. Now, the thing you should notice is that when you take k equals 2, which is the work we did together with Piorkowski, as I said, W vanishes at x equal to -1, and that changes the analysis in a very, very significant way. In this whole business, orthogonal polynomials, integrable systems, the vanishing of a weight at a particular point has a really extraordinary effect. I'll just mention to you the following, that if you look at the KDV equation versus the modified KDV equation, in the case of the KDV equation, the reflection coefficient at 0 energy has a value equal to -1. So 1 minus r mod r squared is 0. But when you're dealing with the modified KDV equation, the reflection coefficient is not equal to something strictly less than 1. This has a massive physical effect on the behavior system. The KdV equation, as opposed to the modified K division, has a whole new regime of behavior called the collision shock region. So just putting in 1 0 into the problem completely can change these kind of problems. So I just want to give that perspective. So, all right. So in order to prove these results, we use Riemann-Hilbert nonlinear steepest descent methods, or RHNSD methods. However, as we will see, the standard Riemann-Hilbert NSD method must be modified significantly to take into account the logarithmic singularity at x equals 1, and also in the work together with Piorkowski, the 0 of W at x equal to minus 1. So what I'll be doing is I'll be trying to explain how Riemann-Hilbert problems come into the analysis of these polynomials, and why there is a form of steepest descent which will allow you to evaluate these Riemann-Hilbert problems asymptotically, and then conclude the asymptotics the behavior of the ANs and the BNs. So I'm aiming towards that. So weights with logarithmic singularities arise in many different situations of physical and mathematical interest. For example, if you look at the Laplacian, the discrete Laplacian on, say, a square crystal lattice, so h u of x is u of x plus delta m, well, delta m is a set of vectors relating a point to its nearest neighbors. And you look at periodic solutions of this problem of period L, and you restrict yourself to the box of size L, and you let L get large. Then you find that the operator H is described by a Jacobi operator with a spectral measure with a logarithmic singularity at 0. So you can see it up there. So you arrive at a problem of that kind. And then, if you look at the Laplacian, for example, on a graphene lattice, one related to a Jacobi operator with log singularities both at 1 and -1 and a 0 at x equal to 0. So, okay. Going back. I don't know where I'm going. Okay. There you see it at the bottom there. And it was this example that really motivated us to say that we have to go from the case where which we worked out with Oliver Conway, where there was no 0 part and just a logarithmic singularity, but to add in a 0, which is what we looked at together with Piorkowski, because of such examples. Okay, so forgive me if I explain these different things. I'm sure it's familiar to many people, but what is a Riemann-Hilbert problem, and how does the Riemann-Hilbert nonlinear steepest descent method actually work? So let gamma be a rectifiable oriented curve in the complex plane. So it's a collection of lines. And to each segment, you attach an arrow, the direction. And then by convention, if you move along a segment in the direction of the arrow, the plus sign to any point Z lies on the left, and the minus sign lies on the right. So if you go along here, your plus side is here and your minus side is there. So I say the plus minus side at a point Z in the lattice lies to the left, or respectively the right side, as one moves along gamma in the direction of the orientation. So let V of Z and B of Z be an invertible n by n weight matrix or a jump matrix on gamma. And we say that M of Z is a solution of the Riemann-Hilbert problem with contour gamma and jump matrix V if the following conditions are true. M of Z is an n by, so V is n by n. So M of Z is an n by n analytic function off the contour. And when you're on the contour, M plus of Z equals M minus of Z times this jump matrix V, where M plus minus is the value of M of Z prime as Z prime approaches Z either from the plus side or from the minus side. So Z prime up here is approaching Z from the plus side. Here Z prime is approaching Z from the minus side. This is the jump relation. So a Riemann-Hilbert problem is a problem about analytic functions which have jumps across, certain prescribed jumps across the contour. If you, M of Z, over here, I don't want to have any problem with it. So if M of Z goes to the identity, why am I having a problem with this? Should be.
I think it's just a little thing. Oh,
okay. So if M of Z goes to the identity, as Z goes to infinity, we say that M of Z solves the normalized Riemann-Hilbert problem, sigma B, and you can get uniqueness in a situation like that. So the Riemann-Hilbert problem, gamma B, can be solved in the following way. How do you solve a Riemann-Hilbert problem? You introduce the Cauchy operator on gamma. So you, given a function f, you integrate the function f of s divided by s minus z ds along the contour gamma, always integrating in the direction of the orientation of the arrows. And then under appropriate conditions of gamma, bring in here the idea of a Carlson curve. The notion of a Carlson curve is one of the most impressive and beautiful concepts within mathematics, because what it is, it's a pointwise condition on a contour, which is necessary and sufficient that the Cauchy operator, this operator here, is a bounded operator in LP. So, and we will come back to that. It's work which started with Calderon, developed by Koifman and many other people, and in particular, most recent at the final stage by Guy David. But it's really one of the most beautiful pieces of mathematics. It's this what Barry Simon likes to call a perfect theorem, one in which you have if and only if conditions. So if you define now C plus minus of gamma f, it's the limit of this object here as the point Z prime approach Z from the plus side or the minus side. And if gamma is a Carlson curve, for example, you know that this limit will exist for almost every point on the contour. And moreover, this operator here will be a bounded operator in L2 of the contour. In fact, in LP of the contour for any p bigger than 1 and less than in infinity. And I ask you to remember this important relation that C plus minus C minus is the identity operator. So what I'm going to show now is that the solution of a Riemann-Hilbert problem is really equivalent to solving a singular integral operator equation on the boundary. So define CV of f as C minus, this operator acting on f times V minus 1. VV minus n. Remember, V is the jump matrix along the contour. Now, suppose mu is a function which belongs to 1 plus an alpha function and solves this equation over here. So suppose you have solved this equation. This is a singular integral operator because it involves this s minus z sitting in the bottom there. Now suppose that mu solves this equation. Here I is the identity n by n matrix regarded as a constant function throughout the contour. Then you define M of z as 1, the identity matrix plus the Cauchy operator acting on mu times v minus 1. So it's this 1 plus 1 upon 2 pi r integral along of mu of s times v of s minus 1 upon s minus z. And clearly, as s goes to infinity, this is going to go to the identity. Now comes this really fascinating little calculation. Suppose I take this function here, which is clearly analytic off the contour. And I value the m plus of at the point v. So it's I plus c plus of mu times v minus 1. But c plus is equal to c minus plus the identity. So c plus is c minus, and the identity just gives you this thing back again. And so you have here the mu v minus 1 minus mu. And okay. So now you observe, going back here, that mu solves this equation. In other words, the identity matrix is equal to the identity plus CV mu is just equal to mu. So let me just write that down. So if I write down like this, I get 1 plus CV mu is equal to mu. So using that, okay, it's 1 plus C minus this thing over here is just mu. And here I got mu v minus 1, which is mu v minus 1. So the mu drops out, we just go mu times v. But if I compute m minus v, that's just 1 plus C minus, which is exactly what I get from here, it's just mu. So if for mu here, I just substitute it in here, and I've got the m plus equals m minus v. And as m of v goes to 1, as v goes to infinity, you see from a very simple equation, once you've solved this equation for mu, you have produced the solution of the normalized Riemann-Hilbert problem. So everything becomes just an analysis of the singular integral operator. I mean, when you're dealing with complex variables, right, things are analytic, they're boundaries, you expect to be able to express everything about the analytic function in terms of what's happening on the boundary. So this brings us to this point. In other words, the solution of the normalized Riemann-Hilbert problem is equivalent to solving the singular integral equation 9.1. That's the equation which we just wrote down. Now, in a seminal development in the early 1990s, Piorkowski and Kataev showed how to solve the orthogonal problem, a polynomial problem, in terms of a Riemann-Hilbert problem. The nonlinear steepest method then gives a way to analyze this Riemann-Hilbert problem asymptotically, and hence the asymptotics of the ANs and the BNs for a given weight mu of x dx. So I'm saying you can convert the orthogonal problem into a Riemann-Hilbert problem, and just as there is a steepest descent method for classical integrals, there is a steepest descent method which will enable to evaluate that Riemann-Hilbert problem asymptotically, and that is a way, a pathway to evaluating the asymptotics of the ANs and the BNs. Okay. So this is the Riemann-Hilbert which they have. So this is the Piorkowski Riemann-Hilbert problem. So let fix n and let y of z, which will depend on n, solve the 2x2 Riemann-Hilbert problem where the contour is the real line oriented from left to right. And the jump matrix is just 1, 0, rho, where rho dx is the weight. Then you also want, in addition to these jump relations, you want it to be normalized in the following, that y of z times e to the minus n, then goes to the identity and then gets low. Now comes this really beautiful formula, or Piorkowski and Piorkowski. We showed that the solution of this Riemann-Hilbert can be written down in the following way. In the 1-1 entry is the monic orthogonal polynomial with respect to rho. In other words, Pn, pi n, pi m, rho of z dz is 0 if m is not equal to 0, and gamma n squared times pi squared is normalized, so pi n, gamma n pi n is the orthonormal polynomial associated with these measures. So just out of the blue, the monic orthogonal polynomial appears over here. This gamma n is this normalization constant. Here, this is the Cauchy transform of the first entry, and here is the Cauchy transform of this entry. That's the solution of the Riemann-Hilbert problem. Now, if you take this combination here and you expand it out, so you'll get identity when z is plus a residue term as z gets large. And the beautiful fact is that the an, the coefficient an corresponding to this weight rho dx, is just given by the 1-1 entry of this residue term for a size n matrix minus the same thing for n plus 1. So there's a similar formula for Bn, which I won't write down. But you see explicitly that if you can control the solution of this Riemann-Hilbert problem as n gets large, you can then just plug it in here and you're going to get the asymptotics of the agents. Okay. So that's in order to repeat myself, in order to evaluate the ANs and the BNs as n gets large, we must evaluate the solution Yn of this Riemann-Hilbert normalized as an equation of level. In other words, Yn z to the n, z to the minus n goes to the identity. This is conveniently done using the nonlinear steepest ascent method, which I'm now going to describe. So everything I'm going to do for the next couple of minutes is just going to show you how the nonlinear steepest ascent method actually works. So for a weight rho of x dx or minus 1, how does the NSD work? So let f of z be the so-called Zago function for rho. So you take rho, you divide by root of 1 minus s squared, ds of s minus n, and you bring this out from the function. This is a function which is defined for z away from the interval minus 1 to 1. You introduce this companion function phi, which will also be analytic off the cut, minus 1 to 1, and behaves asymptotically like plus 2z. And what one notes is that a simple calculation to say that if you're off the interval minus 1 to 1, the norm of phi of z is bigger than 1, and when you're on the cut, you think of z is e to the I theta, then this is going to be something like cosine theta or sine theta. So, okay, plus, okay. So the norm will be 1, but off the cut, it's strictly bigger than 1. So now the steepest ascent method works by a constant sequence of changes of variable. So the first thing you do, here's your solution, y of z, this one over here. Here's your function f. So you look at f of z upon phi to the power n, raised to the power n times sigma 3. So this is a matrix where sigma 3 looks like that. And on the left here, you take 2 divided by the asymptotic limit of this object. That's T of z. Clearly, T of z has the same analyticity properties as y, because phi, this function here, phi, this is analytic off the cut, and f of z is also analytic off the cut. So you're multiplying something which is analytic off the cut by a variety of objects which are analytic. So you haven't changed the analyticity. All right. So then you find that P of z solves the following Riemann-Hilbert problem. T of Z remains analytic off the cuff, but now the jump matrix changes. So this is just a calculation. You've got the jump matrix for Y, so you just do this conjugation and it gives you this formula. T of Z goes to 1 as Z goes to infinity, and T of Z has specific behavior at plus or minus 1, depending on the behavior of rho of x as x goes to plus or minus 1. Now, the difference between whether rho vanishes at -1 or does not vanish at -1 is that there is behavior as x goes to minus where this function t is no longer in L2. That presents a technical difficulty. I just want to raise it at this point. Okay, so everything depends on the following calculation. If you take this matrix here, and you see that it has a factorization which looks like this. So these objects here can all be continued analytically to the minus side below, assuming that rho is something like our W, which has these analyticity properties. This object here has an analytic continuation to the plus side. And what that means is that, okay. Okay, with it, I think I've lost it. Okay, there it is. No, that's gone too far. Okay. With this, we can do the following. This means that if we, what's called open the lenses. So here is your interval from -1 to 1. You put an additional contour up here, additional contour here, so you open up the lenses. Outside the lenses, you define Q to be this T of Z, which is analytic there. But over here, you've taken the piece which we had over here. I'll keep doing that. You take this piece here, or this piece here, which is analytic below, and you move it down. You deform it down, and this piece you push up. So that just means that you define Q to be the original T times the thing which you push up from the right-hand side. This thing is what you push down from the other side. And this is the thing to really watch now. What does Q of Z look like? It's analytic. It's solved the Riemann-Hilbert from on this contour, which are called sigma. Sigma 1 is the top piece, sigma 2 the bottom, and you got this integral from -1 to 1. Q of Z will be analytic everywhere off this contour. But the jump matrix looks like this. So when you're up here or you're down here, it looks like this. And you remember that phi has got a modulus strictly bigger than 1 when you're off the real axis. So this means this object here is going to 0 exponentially. On the contour -1, you're just left with this middle piece. Q of Z still goes to 1, and there's some specific behavior which we have to take into account at plus or minus 1. But at this point, the method is clear. This is because, as I say, phi of Z is strictly bigger than 1 on the top contour and the bottom contour. And this means that the Riemann-Hilbert problem just converges to a simple Riemann-Hilbert problem with a simple jump across -1 to 1, which looks like this. This Riemann-Hilbert problem with such a jump can be solved explicitly. But now, there's a rub in the whole business. That is that as Z gets closer and closer to plus -1, although phi of Z is still bigger than 1, it gets closer and it gets closer and closer to 1. It's no longer strictly bigger than 1. And the convergence as n goes to phi is not uniform. That's a problem. because you need uniform convergence. So the standard nonlinear steepest descent method approach to this canonical obstacle is to localize the Riemann-Hilbert problem around plus and minus 1. One solves the local Riemann-Hilbert problem exactly with appropriate solutions. So you solve the Riemann-Hilbert problem, this little box with the same jumps across here, and another one over here. And away from these disks, one just solves this trivial Riemann-Hilbert problem. This gives what's called a parametrix for the problem. P of z is the little thing which you had in the left disk, and the thing in the right disk, and the thing away from it. So it's away from the disks and away from the line joining them. And the method then works simply because if we set R of z to be the ratio of Q times P of z times this parametric, we obtain a Riemann-Hilbert problem for R with a jump matrix V, which is very close to the identity. You've essentially solved the Riemann-Hilbert up to small terms, which again can be solved explicitly to any desired order. So if you put this all together, it means the solution you're looking for is this parametrix, which is explicit, times this R, which is essentially 1. And it means that Q is now analyzed, and we can obtain the asymptotics for AN and BN from this expansion, because this residue term is going to contain the information about the ANs and the BNs. Now, that's how the thing works. You solve the problem locally around these places where the decay is not uniform, and you just factor it out in this particular way. So that's the way the standard, nonlinear steepest method works for orthogonal polynomials. Now, the essential difficulty now, which comes up, which arises when rho is of this form, the k is bigger equal to 2, and this is the big thing. There is no explicit solution for the local Riemann-Hilbert problem around the logarithmic singularity. One cannot draw a little disk around it and solve that problem locally. If you try and scale it, you just get a bigger version of the same problem. You don't know how to do it. So there has to be some workaround. So what is the workaround? At the same time, at the left-hand point, you have this algebraic type singularity, and it's well known how to construct the local local solutions of the Riemann-Hilbert problem around x equal to minus. Okay. Now, the workaround, the difficulty is based on the solution method for a Riemann-Hilbert described earlier. Remember what we wrote down? We looked at this equation. 1 minus CV mu, and which means that mu is the resolvent times the identity. And if you take that mu and you plug it in here, you're going to get the solution of the Riemann-Hilbert problem. So the workaround is going to use, rather than this business of constructing local parametric, it's going to go directly to the singular integral equation, which can be used to analyze the Riemann-Hilbert problem. So we consider auxiliary Riemann-Hilbert problem. For the case when k is bigger than 2 is the case we looked at with Conway in the beginning. This is the case where w does not vanish at minus 1. We consider the Legendre polynomial case where w is just equal to 1 on the interval minus 1 to 1. It's kind of a mystery that such a potential, which is constant, is an approximation to the logarithmic potential. It's strange, but it is. This is effectively a constant. The logarithm is such a weak function, it's effectively constant. And this turns out to be a good object to approximate this in width, but that'll become clear later. However, for the case where k is 1, we consider two auxiliary problems. One is this w tilde, for a reason I'll make clear a little later on, but also you introduce such a weight which is a algebraic. It's called a Jacobi polynomial case, and it vanishes at -1. And the things to note is that as W hat vanishes at x equals -1, it does so just as W itself does when you put k, and so W hat, as opposed to W tilde, compensates with W near x equal to -. They both have a 0 -1, which is an important element. So both W tilde is this constant weight, and the Jacobi case, the asymptotics of the recurrence coefficients are known. They're well known. Work of Kalos and his group. So to begin to put this together, we have the following. So in view of this relationship here, in view of that, to control mu, and hence M, which is the solution of the agreement problem, and NQ, we must get uniform control on this thing where V equals V and as N goes to infinity. This becomes the essential game that you have to work with. So let me just point this out to you. You really need to control this resolvent to be able to control mu and hence to control M. So we do, in the case where W has this singular, where it has a 0 at -1, we solve the Riemann-Hilbert problem locally around -1 for these three different weights. So W tilde is just the weight which is equal to a constant. W hat is 1 plus x, it vanishes at -1, and W x equals k equals 2 is the one we're interested in. Both of them, all three of them, have a local Riemann-Hilbert problem around -1, which can be solved explicitly. So you deform the contour from here to here. But now what you do is you want to somehow remove your focus from the point 1 where the logarithmic singularity is. So you take this contour and you fold it back out again. So the point 1 is now sitting in the middle here, and you're at some point for delta bigger than 0 in a contour which looks like that. Now, the fundamental fact why this is a good thing to do is the following, is that you have removed focus completely from the two pressure points. The pressure point is where this vanishes at -1. The problem is removed over here. It's removed. And now by moving it away from here, you've removed the logarithmic behavior. In a sense, there's nothing really conceptually different on this contour between these three different weights. They might differ a little bit about concept or not, but essentially their analytic behavior is going to be the same, which means that if for one of them you can control the subsequent n, you're going to be able to control the resolvent for the other two as well. And that is what one does. One, on the final contour, and this turns out to be a fundamental factor, then we control this resolvent asymptotically as n gets lower for this Legendre weight. It's very simple. Now, a really interesting part of mathematics comes in here, because you need to know that not only is this operator bounded in L2 of the contour, but also where the contour has Markenhaupt weights. That's a feature of the Carlson curve. So weighted versions of the Percy operator are also bounded in L2, and one uses that here. But now on sigma delta, there are no great differences, as I've been saying, between these three different weights. So the 0 of W at equal -1 and the logarithm at +1 are elided from the contour. And this allows us to control 1 minus CBM also for W hat and W, because it's not really that different from the constant. A fortiori, we can control the difference between, for this operator, for W hat and for W. And then that means we can obtain the asymptotics for our desired weight over here from the asymptotics for W hat, which are known. And that's how one controls the problem. Okay, I'll stop.
Maybe a quick question. Can you is next speaker again?
We don't spread out, so.